All right, BC Calc, this is going to be your day 67 notes. We're going to continue our discussion of work today, and we're going to bring back some Hooke's Law type examples and then extend this concept of work even a little bit further. So if you look at the first page, this is just a recap of some things that I think you should know how to do. One's just a quick arc length here for the function y equals ln of 1 minus x squared. Find the length of the arc from 0 to 1/2. So you can try that one for me before I see you next. And then there's a think about it down here that relates to what we talked about yesterday in terms of the work that's done in each of these instances. Okay, so you can see the graph shown where the force in pounds that is required to move an object 9 feet along the x-axis. And you want to try and figure out the order of how much work is done from the least amount of work to the most amount of work. So I think that will be pretty easy for you to establish once you take a look at those graphs down there. Let's get right to the next page where we're going to do our recall of Hooke's Law. So Hooke's Law from yesterday is the force required to stretch a spring. And the formula we have is that the force equals K, some constant of proportionality, times X. So the work that's done is going to be the integral from A to B of our function f of x dx, where f of x is kx right there. So if the force equals 6 newtons at 0.4 meters from equilibrium position, how much work was done? So in order to determine work, we need to figure out what is our constant of proportionality, which we don't have. And I'll tell you, it seems pretty often that we won't be given that information necessarily. So to figure out the constant here, if the force is equal to kx, we know that the force is 6 when the distance is 0.4. So if you divide the 0.4 over, we get that k is equal to 15 for this example. And once you get that k is 15, to figure out how much work was done, we're figuring out the integral from 0 to this distance, 0.4, for the function 15x dx. So once we set up the integral to determine the work here, we're going to up this by 1, x squared, divide by 2 out front. So the antiderivative is 15 halves x squared. Plug in the upper bound of 0.4, plug in the lower bound of 0, and it turns out that the amount of work that was done is 1.2 and Newton meters. I'm sure you guys are familiar with this. If you're taking physics, would be 1.2 joules at that point. That's the amount of a unit of work. We're dealing with Newton meters here. Okay, moving on to example 2. Example 2 is a new look for us today. This is kind of like a type 2 work situation because we already know how much work was done in a given instance. If 100 foot-pounds of work was necessary to compress a spring 2 feet, how much work is necessary to compress the spring another 3 feet? So we're given a certain amount of work that was already done to compress 2 feet, and then I want to go another 3 feet beyond that. So we're going to have to figure out what is this function that we're going to be integrating, but we already know what the work is to get to 2 feet. So the work would be the integral from 0 to 2 of the function kx dx. We already know work is 100 over here. So what this is going to allow us to do is if I integrate the function kx dx, where we know k is some constant, we can use our definite integral with our upper and lower bounds here to determine what k is based on knowing what the work is. So this is going to become 100 equals, well, the integral of kx dx, remember k is just constant, so it's going to be x squared over 2 here. So k times x squared over 2 from 0 to 2. If I plug in the upper bound of 2, we're going to get 2 squared over 2. So let's see, 2k is equal to 100. And therefore, k is 50. So a little bit of a sneaky way to find that constant of proportionality. This one was maybe a little bit more direct and similar to what we saw in yesterday's notes. But now that we know that the constant k is 50, we want to figure out how much work is done. So setting up another definite integral to compress the spring another 3 feet. So if we've already gone 2 feet to get to another 3 feet, we're going from 2 feet to 5 feet for our function 50x dx, now that we know what k is. Okay, so the amount of work that was done would be equal to, let's see, up that by 1, so x squared divided by 2, 25x squared is the antiderivative. And then from 2 to 5, plug in the upper bound, plug in the lower bound. It turns out for example 2, The amount of work that's done to compress the spring another 3 feet is 525, and our unit here, again, sounds a little weird, but we have that many foot-pounds of work that was accomplished to compress the spring another 3 feet. And by the way, if you feel pretty confident setting these up, certainly at any point you can stop the video and try them and then kind of fast forward to checking on your answers once you're done. The last example is a little bit different in that we're talking about a ship's anchor weighing a ton. And then the anchor chain weighs 50 pounds per linear foot. So what I'll tell you is that in this example, the weight in this case is equal to the force. Okay. So that's going to, I think, just be a little bit helpful in terms of making a setup here that if the ship's anchor weighs 1 ton, the anchor weighs 50 pounds per linear foot. That weight that we're talking about here is the force in question. So to figure out the work, we're going to integrate that force. But we have to define what it is. And we want to pull the anchor 100 feet of chain is let out. So we have to pull in the 100 feet of chain to get the anchor back on. So the work that we're going to be done is going to be integrating from 0 to 100. And then what is that force if it represents the weight in question? Well, it's 1 ton plus 50 pounds per linear foot. 1 ton is that fixed weight, which is to make sure we do a quick conversion over to pounds. 1 ton is 2,000 pounds. So the weight, the function that we're integrating is 2,000 to start plus 50 pounds per linear foot, so plus 50x dx. And once you know that the weight is representative of the force here, setting up that definite integral hopefully isn't too bad for us. Finding the value of the definite integral will be pretty easy as well. 2,000x plus 25x squared. Plug in the upper bound of 100, lower bound of 0 will give you that the amount of work that it takes to bring the anchor in is 450,000. Sounds like a lot of work here. Foot-pounds. Okay. So these are all very similar setups in terms of work examples that relate back to Hooke's law from yesterday. And there were those other 2 laws that we talked about as well with Coulomb's law and the universal gravitation law. So we won't see those come up as much as we will with Hooke's law, but if we do, we can certainly work with those as well. All right. If we're good with Hooke's law, we're going to move on to a new type of case today, where we're going to figure out how much work it is to remove a liquid from a given bowl. Okay. So it's kind of an odd case, but let's read through it. It says a parabolic bowl. Everybody has some parabolic bowls with a cross section of y equals x squared is filled with a fluid. Okay, and this fluid of density is 60 pounds per cubic unit. I'll give you a reference point in a moment to talk about a fluid that we know the density of for comparison purposes. If the bowl has a height of 4 units, I guess, how much work must be done to remove all of the fluid from the bowl? So we have to start building a case here where if we're trying to figure out how much work was done, we have to connect it to what we know about work and forces and weights and all those things. From the last example we just did with lifting the anchor, the weight in that example was the force. So we'll connect to that in a minute. But something else that will be useful to talk about is we're given a density. The density is 60 pounds per cubic unit of the fluid. So density is defined as a weight per unit volume. So in order to connect back to what we just did, where the weight is equal to the force, how am I going to find the weight in this case, which again is representative of the force that we're going to integrate? Well, to figure out the weight, if we know the density, we're going to take the density, and you can imagine if I take density and multiply by the volume, those volume parts would cancel and I'd just be left with weight. So that's exactly what's going to happen. To figure out what the force is, which is the same thing as the weight, we're going to take the density and multiply by the volume. So the density, which we're given in this case, how would we find the volume? Luckily, we have a lot of techniques to find volume at this point. So if we think about what this parabolic bowl would look like, the diagram's going to look something like this, right? and we have this liquid that we're going to try and remove from the bowl. Okay. And by the way, the liquid that I wanted to compare to is if you have water in the bowl, that's 64 pounds per cubic unit. Okay, so just as a point of comparison there. But I mean, it's tough to slice through water, isn't it? So I think the best way to think about this is think of this as like a parabolic bowl of Jello. Okay, and we're removing the Jello from the bowl. So how do we find the volume of that? Well, this is a pretty easy case for volume by disk, isn't it? Okay, so you can see our disk that I have drawn in here, and we have to think about what the radius is. So we have y equals x squared. Okay, but the volume is going to be from spinning the disk around the y-axis. So we might want to get x in terms of y, and that's exactly what I have here. So if y equals x squared, we know that x is the square root of y. So there's my radius. Radius is radical y. Okay, and we're going to start building a case now, thinking about the fact that we have the volume, and we know what the density is. The density is 60. Okay, so from here, the weight of one slice would be the force. So we're talking about the force, which is this weight component over here, times the distance that it takes to remove this liquid from the bowl. Okay, the weight of a slice is going to be the force times the distance. So the force is this right here. It's the density times the volume. The density was given as 60. And then the volume with our disk method would be pi r squared. So that's pi times radical y squared. And then what is the distance that it takes to take this liquid at any given moment and remove it from the parabolic bowl? Well, that distance is going to be 4 minus y. If the height is 4, at any given y value, the distance that we have to remove the liquid would be 4 minus that y value. Okay, so now that we have the force and we have the distance, we can write this as the definite integral from 0 to 4. Okay, we're integrating, remember, if we're doing this with respect to y, these are the bounds along the y-axis of 60 pi radical y squared, just y, times the distance 4 minus y, dy. And once we have that set up, it's pretty easy to integrate, but I think taking some time to really understand where we get this from might take a little bit more consideration. And 60 pi, of course, is a constant, so you can bring that to the outside because now you're integrating 4y minus y squared. Okay. So in the end, if you do this calculation and find the antiderivative, you get that the amount of work that's required to remove the liquid from this parabolic bowl is 640 pi unit pounds. Okay. We're going to talk a little bit more about this specific example and kind of break it down into some other scenarios. But I would say definitely take a look through this example again and make sure that the way that we derive this makes sense to you, right? So to find work, it's that force times that distance. So the work that's required to move the water here, the force times the distance. If we integrate along those bounds along the y-axis, we get how much work was accomplished. Okay. So if we move on to the next follow-up question to this scenario, next follow-up says, is it more work to lift the top half or the bottom half of the liquid? So going back to my parabolic bowl. Okay. Okay. So halfway up along the y-axis would be at 2. So the bottom half would be the same integral that we just set up, but just only over the bounds from 0 to 2. So to get the bottom half, you would take out your 60 pi, remove that again, and integrate from 0 to 2 the function y times 4 minus y dy. And let's use the calculator to help us figure out what that is pretty quickly. So math 9 will go from 0 to 2. And let's see what we get when I multiply this by 60. So times 60 is 320 pi. And this would be unit pounds. So that would be the amount of work that it takes to remove the bottom half of the liquid. Make a prediction right now before we do this part. Do you think it's going to be more work to remove the bottom half of the liquid or the top half? I mean, the bottom half has a longer way to go to get out the liquid. But in the top half, this is going to be holding more liquid. So, I don't know. Make a prediction. Which one do you think is more? Because then the top half is 60 pi times the integral from now 2 to 4 of y times 4 minus y dy. Okay, so let's see what this comes out to be. So we'll do 60 times. Let me go back and grab this integral actually, because it's the same thing, just with the bounds from 2 to 4. So if I change those bounds 2 to 4, it turns out, and maybe you made this guess yourself, that it takes the same amount of work. That is also 320 pi unit pounds. So it is the same amounts, which is pretty cool. Okay. Now, clearly, if we change the shape that our liquid's being held in, that might change if the bottom half or top half takes more work to compute, which might happen in a future follow-up in just a moment here. But how much work is it to lift all of the liquid 2 units above the top of the bowl? So if we think about where the top of the bowl is at a height of 4, I now want to take all the liquid and I want to somehow lift it to a height of 6 instead of that height of 4. Okay, so if I think about this as force times distance, it's not that the force part is changing at all, right? The density is still the same, the volume is still the same, but the distance that you're moving all of that's what's really changing here, right? So in order to compute the integral in this case, the distance in which we're moving the liquid is what's changing. So instead of having the distance of 4 minus y, now we have a distance of 6 minus y at any given moment. So let's see how much more work it takes. Definitely going to take more work to lift the liquid 2 units above the top. So 60 pi times the integral from 0 to 4 of y times 6 minus y dy. And in the end, let's see what we get here. So 60 times, actually I could probably steal this and make some quick changes. So we want to go back from 0 to 4, but now we want it to be 6 instead of 4. And it appears that we have 1600 pi unit pounds. Okay. And if you compare this to what we had with just lifting it to the top of the bowl instead of 2 units above, this is a 150% increase in the amount of work that we had to compute there. All right, 1600, what was the other one? 640, is that what it was? Yes, 640. So 1600 minus the 640 over the original is 1.5. So 1.5 times or 150% more work was done to lift the liquid 2 units above. Last thing we're going to do with this removing and the liquid from our bowl is change the bowl. Okay, so we're going to change it to, instead of having a parabolic shaped bowl, let's have a cylindrical container. Okay, so think about what's going to be the major difference here if we have a cylindrical container as opposed to our bowl with the parabolic cross section of x squared. So in this example, cylindrical container has a radius of 2 and a height of 4. Okay. Okay. When I think about setting up my integral in this case, to figure out the weight, which is our force times the distance, the force, remember, is the density times the volume. And what happens here is, since the volume is the same at any given instance, it's not going to change. We don't need that disk method anymore, right? Volume would be pi r squared times the thickness dy. And since the radius is constantly 2, we get that the volume is going to be 4 pi times the thickness at any given slice, right? So if I think about making these slices here, Okay. These are always going to have some sort of radius of 2 no matter what. And then some thickness dy. And the distance is still going to be, in this case, because the height of the cylinder is 4, the distance is 4 minus y. So if I take my volume multiplied by the density of 60, we're going to take 60 times 4 pi, which is 240 pi, and pull that constant all the way to the outside. So this one's going to be, to calculate the work that's computed here, 240 pi times the integral from 0 to 4 of now just that distance, 4 minus y, that's all that's left, dy. So how much work was done here? I don't know, let's see. So it's 240, and then the integral from 0 to 4, 4 minus x dx is 1920. Okay, so 1,920 pi. If we compare this to what we had in our case where we had the parabolic bowl, this one is 200% more work to accomplish. Okay. So a lot more work to get the liquid out of the cylindrical container as opposed to the parabolic shape bowl, which makes sense. Okay. All right. Last thing I want you to do is the same exact follow-ups that we did with our parabolic bowl. I want you to try and do them, or at least set them up in these follow-up questions. So how much work is it to remove the top half of the fluid versus the bottom half of the fluid? And again, we're talking about for the cylindrical container. And then how much work would it be to lift all of the fluid 2 units above the top of the cylindrical container? 2 examples, 2 follow-ups that are pretty much the same type of follow-up as what we did with the parabolic bowl. So set those up. We'll talk about them next time I see you in class, in addition to those warm-up questions at the start of the notes. All right, more work day 2 for you here. Let me know if you have any questions.